Hi everyone, welcome back to my video about programming in Go. This video is the second part in the series on topic number 3, methods and interfaces. In the first part, we had covered methods, and so in this part, we will cover basics about interfaces. An interface is a data type that is defined as a set of method signatures. But what is a method signature? A method signature is the declaration of a method that consists of only the method name, the list of arguments, and the return type. It does not include the receiver argument. For example, apps parentheses flow64 is a method signature with method name apps return type flow64. This method doesn't take any argument. Then here, appser is an interface type that consists of the method signature apps. To define an interface type, we write the keyword interface after the type name and followed by the list of method signatures enclosed in braces. Since an interface is a type, it also has values. A value of an interface type can hold any value that implements those methods. For example, here we define time myFloat to be the building type flow64 and define a method with the same method signature as the one in the appser interface, but with the receiver of time myFloat. Then any value of myFloat is set to implement the apps method and therefore is a value of the interface appser. Similarly, we define the struct type vertex and define a method with the same signature as the one in the appser interface, but with the pointer receiver of type pointer to vertex. Then any pointer to vertex is also a value of the appser interface. In this example, f is a value of myFloat and v is a value of vertex. So both f and %v are also values of appser and therefore can be assigned to the variable app, which is declared to be of type appser. Recall that %v is a pointer to v, which is of type pointer to vertex. Note that here the value v of type vertex is not a value of appser because the method in appser is not implemented with a value receiver of time vertex. It's only implemented with a pointer receiver of time pointer to vertex. Note that interfaces are implemented implicitly. By definition, a type implements or satisfies an interface by implementing all its methods. There's no explicit declaration of intent, no implements word, and implicit interfaces decouple the definition of an interface from its implementation, which could then appear in any package without pre-arrangement. For example, in this program, we have the interface I that has only one method signature M, and we have a struct a type named T. And so then we have the method with the method name M, and with the receiver of time t. So this method means time t implements the interface I. So there's no word implements and nothing that clearly to say that time t implements the interface I. The implementation of time t of the interface I is implicitly declared by the existence of this method. There are many built-in interfaces in Go's standard libraries. One of the most ubiquitous interfaces is Stringer, defined in the uh, FMT package. Here is the definition of the Stringer interface in the FMT package. It consists of only one method named string with the capital S. This method takes no argument and returns a string. A stringer is a type that can describe itself as a string. The FMT package and many other packages look for this interface to print values. As an example, let's define a struct type named person. This struct has two fields, name of time string and age of time int. Then we define a method with the same signature as the one in the Stringer interface, but with the receiver of type person. This means type person implements interface stringer. In the definition of this method, we call the fmt.printf function to format according to a format specifier and return the resulting string. The string returned by this method consists of the name and age of the person receiver. In the format, start with the name followed by age, then years, enclosed in parentheses. In the main function, we declare a person value A with name equal Alex Dent and age equal 42. Then we print out the value of A using the println function. Note that if the struct person does not implement the stringer interface, then the fmt.println of A function will print out the value of A in the standard format, which is without any parentheses and without the word years. But because the struct person implement the stringer interface, this println function will display the value of the person A in the format specified in the definition of this method. That is the name, Alex Dent, and then open parentheses, then the year, which is 42, and then the word years, and then close parentheses. An interface is actually an abstract type. What does that mean? It means that when you have a value of an interface type, you know nothing about what it is. You only know what it can do. In contrast, when you have a value of a concrete type, you know exactly what it is and what you can do with it. All the times we have looked prior to interface or concrete types. Under the hood, interface values can be thought of as a pair of a value and a concrete type. An interface value holds a value of a specific underlying concrete type, And calling a method on an interface value executes the method of the same name on its underlying type. This example illustrated the interface values under the hood. In this program, we defined an interface I which has only one method signature M. Then we define struct type T which has only one field S of time string and define type F to be float64. Type T implements interface I by implementing method M with a pointer receiver of type pointer to T. This method just prints out the field S of the receiver. Type F implements interface I by implementing method M with a value receiver of time F. This method simply prints out the value of the receiver. In the main function, we declare variable I of the interface type capital I. Then we assign a pointer to T a pointer to T value to variable I. So now variable I is holding a value of the underlying concrete type, which is a pointer to T. And calling method I dot M will call the method M on a pointer to T. Here, function describe takes an interface value I as argument and displays the underlying value and type of I. Then we assign an F value to variable I. Then it becomes holding a value of the underlying concrete type F, and calling method I.M will call the method M on the given F value. Recall that an interface value is a pair of an underlying value and a concrete type. That underlying value can be nil. If the concrete value inside the interface value is nil, the method will be called with a nil receiver, but the interface value is itself non-nil. As an example, let's modify the method M of the interface I that the struct T implements. In this method body, it first checks if the pointer receiver T is nil, and if so, it prints out the string nils. Otherwise, it prints out the field S of the receiver T. In the main function, when variable little I and variable little t are declared with the var statements, both of them have nil values. Variable I has the nil interface value of type capital I, and variable little t has a nil pointer value of type pointer to T. After assigning variable t to variable I, then variable t is still a nil pointer, but the interface value in variable I is not nil anymore. The underlying value of the interface value I is a nil pointer of type pointer to T. And when we call I.M, the method M is called with a nil receiver of type pointer to T, so it displays the string nil. In some languages, this would trigger a non-pointer exception, but in Go, it is common to write methods that gracefully handle being called with a new receiver as with the method M in this example. Back to the main function. When we assign a non-null pointer value to variable I, then the underlying value of the interface I is not null. So when we call I.M, it is called with a non-null receiver and displays the field S of the receiver. So the interface values with a null underlying value are not the same as the null interface values. While the former one still holds a concrete type, a null interface value holds neither value nor concrete type. Therefore, calling a method on a null interface value is a runtime error because there is no type inside the interface tuple to indicate which concrete method to call. For example, when we declare variable I to be of type capital I, which is the interface type with only method signature M, then variable I is a null interface value. Both its underlying value and the concrete type are null. So when we call method I.M, it ends with a runtime error. Now I'd like to show another popular built-in interface, which is error. The interface error serves as the standard for handling and representing exceptions in Go. Functions in Go often return an error value, such as function run in this example, where a null error indicates success and a non-null error denotes a failure. The built-in interface error is defined similarly to the interface fmt.stringer. It has only one method signature named error that takes no argument and returns a string. Any type that implements this interface can be used as an error. You can define a custom error type by implementing the error method on any struct. This allows you to include additional contextual information beyond just a simple string, which is useful for debugging. For example, we defined myError struct, which has two fields, when and what. The field when is a time defined in the time standard package. It's supposed to store the time at which the error occurs. The field what is a string which is supposed to be a description of the problem. Then we implement the error method on myError struct. This method definition simply returns a formatted string with the fields when and what of the pointer receiver. Now my error value is also an error value. So function run, whose return type is error, can return a myError value with when equal the current time and what equal the string it didn't work. As with the fmt.stringer interface, the fmt package looks for the error interface when printing values. For example, when we call function run and print out the error value it returned, the fmt package looks for the method error of the underlying error value. In this case, is the method error of myError struct. So fmt.println of r will display the current time and the string it didn't work. If a function returns an error value, the calling code should handle errors by testing whether the error equals nil or not. Recall that a nil error value denotes success and a non-nil error denotes failure. For example, a function a2i in the strcount standard package takes a string as argument and converts it to an int value. But sometimes the string cannot be converted to an int value, so therefore it also returns an error. So when we call this function, we always have to check if the returned error is non-nil or not. If it's not nil, then it cannot convert the given string into the int value. So in this video, you have learned that an interface is simply a set of method signatures and is an abstract type. A type implements an interface by implementing all its methods. And you have also learned two built-in interfaces, including the stringer interface in the FMT standard package and also the error interface. Thank you for watching, and I hope to see you again in my next video in the methods and interfaces series. Thank you.